is Ryan Marquis, and this is part 2, Fluent 2D flow simulation of airflow over a flat plate. So right now we're in Design Modeler, and first thing we want to do is create what we're going to use for a flat plate. So first thing we're going to do is hit XY plane, then we're going to go into sketching, and we're going to create a rectangle. Once you have the rectangle drawn, we're then going to dimensionalize this. For the horizontal, this project requires us to have a horizontal length of 100 centimeters, which is 1 meter. And our vertical length is going to be half of that. So here's our rectangle. This bottom line will be our flat plate. Okay, now the next thing you want to do is go into concepts, and you're going to hit surfaces from sketches. And then for base objects, you want to hit your sketch, and then hit apply, and then hit generate. This generates our surface. Now you're going to X out of this, and we'll save it, and we'll go on to meshing. Now we're out of Design Modeler, and now we're going to go double click on mesh. We're going to start that up. Okay. We're now in our mesher, so here's our surface. So we're going to go create our mesh. We're going to do a face mesh, and then for geometry, do surface, hit apply. Now hit generate. This is what our mesh looks at the moment. We're also now going to do a sizing. It's going to be an element sizing. So hit the edge one, and then we're going to hit control, and then we're going to select the top and the bottom. And now we're going to hit apply for the geometry. And now for the type, we're going to change this from element size to number of divisions. And for number of divisions, we're going to see what 70 does for now. And for bias type, we're going to set it to no bias. Now we can generate the mesh again. So that's how it split up the mesh. Now we're going to do another element sizing. We're going to change this one also to number of divisions. We're going to do 60 for the amount of divisions. Change the bias type to the top one for now. For bias factor, we're going to set it to 70. And then we're going to generate this one. Now we're going to do the exact same thing for the right side. So we're going to right click on mesh, insert another sizing element, go to edge, control, select which one you want, hit apply. That'll be our edge. Change it from element size to number of divisions. Change your number of divisions to 60. Change your bias factor to 70. And we're going to generate that. You can see now that our bias is actually flipped for our edge sizing. So we're going to have to go into reverse bias and then hit apply. Select the edge, and hit apply. This should flip that bias around, so it should be the correct position now. You see the mesh, we have to make some changes. So the first thing we're going to do is we're going to go into edge sizing. We're going to go into capture curvature. We're going to say no to that, and we're going to keep it as soft behavior. And now for edge sizing 2 and edge sizing 3, we're going to change that from capture curvature and hit no, but we're going to turn the behavior to hard. Same thing with edge sizing 3. Now we're going to regenerate the mesh. Sorry, I made a quick error. We're actually going to change the behavior to hard for everything. And so that should make all these lines vertical and horizontal, and you won't have any curves on any of these lines. Okay, the next important thing we have to do is we're going to have to create name sections. So we're going to right click on the left line, or actually we're going to left click on the right on one of our edges, and then we're going to right click. We're going to create name section. This is going to be our velocity inlet. Hit OK to that. Select the right far edge. And this is going to be a pressure outlet. Next, we're going to name this bottom line. This is going to be our wall or plate, whatever you want to name it. This is what we're looking at the flow over this line. This top plate will be far field pressure. Now you should have a name section drop down, and each one should have one of your name sections. So we have velocity inlet on the left, pressure outlet on the right, we have our wall, and we have our far field pressure. We're now going to X out of this. Now that we're back in Workbench, we're going to go over to Mesh, and we're going to hit Update. We're going to let that update. Once that's updated, the next thing we're going to go is go into Setup. So double click on Setup. We're going to select Double Precision, and depending on how many processors your computer or laptop has, you could decide how many you want to use. I'm going to use 8 for mine, and then I'm going to hit Start. Once everything's loaded up, you can see our velocity inlet and our pressure outlet, and this is what our mesh looks like. So now we're going to go into our mode. We're going to change our viscous model, and we're going to change this one to laminar. And I hit OK. Next thing we're going to do is go into our boundary layer conditions section. Just make sure everything's right. Velocity inlet set to velocity inlet. Pressure outlet is our pressure outlet. We have our wall, that's wall. And then for far field pressure, we're going to want to change this to symmetry. Hit apply. Next thing is we're going to go into our material, go into fluid, select your air. Now what we're going to do is we're going to have to change a couple of these values according to what they want in the file. So air density we're supposed to do is 1.2 kilograms per meter cubed. So we're going to change this to 1.2. And then we also have to change our viscosity. it wants us to have a viscosity of 1.8 e to the negative fifth. Hit change and create. Now we're going to close this. And now the next thing we're going to do is we're going to go into our boundary conditions and go into inlet. And we're going to change this to 2 meters per second because that's what it wants us to do. We're going to hit apply. We're going to close that out. Once we set the velocity, we're now going to go into initialize. And you're going to hit select hybrid initialization and hit initialize. You can also do a standard initialization. You just have to change a few things, nothing too hard, but hybrid's just a little quicker. Okay, initialization is done. So now we're going to go to run calculation. Change your number of iterations. I set it to 100, depending on how fast your scaled residuals converge. You might have to add more, but we're going to keep it at 100 for right now, and we're going to hit calculate. Okay, my calculations were complete, and they converged at 60 solutions. Now, first thing that we're going to do is we're going to get the velocity with vectors and the pressure contours around the plate. Okay, so to get our velocity with vectors, we're going to go into graphics, then we're going to go into vectors. In vectors, we're going to vectors of velocity, and then we can do color by velocity, and we have our velocity magnitude. You're going to want to select interior surface body, and then we're going to compute it. I'm going to save and display. So here's our flat plate with vectors, velocity vectors, and now we can zoom in on the boundary layer. And this is what it looks like along the flat plate. So these are the vectors, velocity vectors. Next thing we're going to do is we're going to get our pressure contours. So we're going to go into contours, contour pressure. We can do static pressure, compute, and then save and display. As you can see, here's our contour of static pressure. And zoom in on the boundary layer. And the next thing we're going to do is we're going to get the contour of dynamic pressure. Hit compute, save and display. Here's our contour of dynamic pressure. We can zoom in on the boundary layer. Okay. Now we're going to change dynamic pressure. We're going to do absolute pressure. Compute it, save and display. This is what that one looks like. Now for our last pressure, we're going to do total pressure. Compute, save and display. Okay, now we're going to work a little out of order. So instead of applying the velocities right away, the next thing I'm going to do is get the drag coefficient for the flat plate using Fluent. So the first thing you're going to do is you want to go into reference values. So reference values can be found right above your solution. And reference values, you're going to have to change your density. I already changed it, so as we said earlier, instead of doing 1.225, we're doing 1.2. This is in Australian kilograms per meter cubed, as you can see right here. You're also going to want to change your velocity. So our velocity for this is going to be 2 meters per second. We're going to have to change our viscosity as well, since we changed it earlier, because that's what they wanted. Everything else you can ignore. Once you have this, you can now accurately solve for your drag coefficient. If you didn't know how to do the reference values and change those accurately, you could always take your data and export it and then solve it using equations in Excel. But once you do this reference values to get your drag coefficient, you can go into reports, go into forces, select wall, and you want to print. Once that's printed, you go into your console and you'll have your force report. So the drag coefficient will be this last one. Now obviously it's kind of hard to see exactly which one it is. It doesn't have it listed anywhere. So you want another way to find it is you're going to go into report definitions, create a new one, go force report, drag, select drag coefficient, select wall, compute, and OK. And now it should print out in console, and you can see drag coefficient, wall, same exact value from above. So this will be our drag coefficient. So now the next thing we have to do is now plot the wall shear stress and skin friction coefficient along the flat plate using Fluent. To do that, first thing we're going to go into is results, and under results find plots. Once you find plots, find XY plot, double click into that. And for the y-axis function, we're going to change it off of pressure. We're going to go into wall fluxes. And so you can see for the first wall fluxes, we have wall shear stress. Select wall. Now save and plot. You see here's our graph for that. And now to get skin friction coefficient, we're going to change it off of wall shear stress, and you should have skin friction coefficient right underneath it, and you could save and plot as well. So you can see here that is. It's a very similar graph to the wall shear stress. So now what we're going to do is we're going to need to plot the velocity profiles at 35 centimeters and 75 centimeters. We won't do this in Fluent. We're going to do that in CFD post. So now what we're going to do is if you haven't, you want to save this file already. Save the project, and once you do that, X out. And I'll see you in Workbench in a few seconds. Now that we're in Workbench, we're going to go into results. Double click on results and wait for that to load. Now we're in CFD post, which is also the results section of Workbench if you didn't see that. So the first thing we want to do is we're going to go into insert, location, select line. I already did that, so I'm already in line details. And so this is what's going to create our lines at our location of 35 centimeters and a line for 75 centimeters of the flat plate. So we're going to change our x-axis to 35. Oops, sorry, it's going to be 0.35. Same thing for 0.2, 0.35. For 0.1, our y-axis is going to be 0 because we need it at the bottom of the plate. And we know our height of the rectangle is half a meter, so we'll put 0.5 in for that. And then samples is how many points we'll have on that line. So we could do it for 10 for right now. Hit apply. And this should show you the line at 0.35. And this is what we're going to use to get our velocity along that line. Hit line 1. And then you're going to hit duplicate. We're going to get a line 2. And in line 2, we're now change the x-axis. So we have 0.75. And also change it for 0.2. 0.75. Apply that, and now we have our second line at 0.75. Now we're going to want to make a chart, so go to chart, insert a chart. Once we have the chart made, you're going to go into data series. For first series, we're going to do line 1. For our x-axis, for now, we're going to do our velocity in the u direction, and for y-axis, just y. And how to apply. This graph's a little weird right now, and that's because our sampling size for the line was only 10 points. So what we're going to do is go back into sampling size, and we're going to change this to, say, 400 samples. So that's going to divide that entire line into 400 points. Each point will get data, so it should get us a more accurate graph. Hit apply, and we're going to do the same thing for line 2. Now go back into chart 1, and as you can see, our velocity is already looking a lot better at position of 0.35 centimeters. So now go back into data series, and then we're going to hit this, series 2, and now for the location, select line 2, and our x and y is the same. It doesn't change when you add a new series. We can now apply it, and so that's what it's going to look like. And now the next thing we're going to do is we're going to go into expressions, and since most comparisons that for these graphs need to be non-dimensionalized, and Dr. Osby likes to do that, so that's what we're going to do. We're going to create a new expression, and we're going to call it U non-dimension expression. Hit OK for that. Go into expressions, or sorry, variables. Do velocity u, divide. Okay, so I have velocity u divided by 2 meters per second. The 2 meters per second comes from our inlet velocity, so yours probably won't be 2. It depends on what your inlet velocity is, and then make sure you put in brackets next to the 2 your units. In this case, it's meters per second. Okay, once we have that, we're going to go into variables, create a new variable. We're going to call this u non-dimension. Hit OK. Make sure you hit apply if you didn't do that. And now we can go back. Now you should have your non-dimension expression. Hit apply for that. Go back to our chart view. And for velocity, might take a second. It doesn't like to appear on the first time. There it is. U non-dimension. You can apply this, and now you can see they're more accurately around 1. So that's a non-dimensionalized form of velocity. And so you could do the exact same thing in the y direction. In this case, we don't have to because our y is already sitting at 1 meter. So we won't be doing that. But if you have a height that's greater than a meter, then you're going to want to follow the exact same steps we did to non-dimensionalize your velocity. And you could do that with your height. So we're not going to do that. The next thing we're going to do is we're going to make a new variable, or a new expression, sorry. So going to expressions, create new, and this expression we're going to call eta expression. Hit OK. In eta expression, go into variables, select y, and divide the square root. 1.8 for our viscosity, e to the -5th. Make sure you add the units for that and multiply it. by your x value, hit apply. For variables, we're going to create a new one. It'll be called eta. Hit OK. Hit apply. Now we're going to go back to our graph. Okay, so we're not done yet. It looks a little weird. So what eta does is it helps compare our velocity profiles at 0.35 centimeters and 0.75 centimeters to Blasius velocity profile, which is further down. It basically correctly scales it. So what we're going to need to do is we're going to have to go into data series, hit new, and in that data series I'm going to change it to file location. Okay, I think I did make a quick mistake. I showed you that the x-axis was eta. That's not true. It's stays as u non-dimension. Your y-axis is going to be eta. And so for my data series, I imported my file. I made sure my columns were right. And you can see in the green, it's the Blasius solution. So now we're going to go into the y-axis just to make this graph look a little better. Minimum is 0. Our maximum we're going to set to 10. Hit apply. And so here is the comparison between our velocity profiles and our Blasius solution. For the Blasius solution data, to find or to import the correct data, I found a Blasius solution table. I took the nth value and the f prime of nth value. I put that into Excel and I converted it to a .csv file, which is a comma separated value. That file you're able to save and then import into ANSYS, and that's what you're seeing right here. There's also another method. I believe if you flip eta around, you can then solve for, you could convert the Blasius solution more like your original velocity profiles instead of your velocity profiles converting to to look similar to your Blasius profile. So there's different ways you can do it. Each show you the similarity between the two, and this is the one I chose. That should be all for the data for part 2. Like I said, this is all the data for the Fluent for part 2. The theoretical was solved in Excel and then was later compared to these values, and you'll be able to see that in our final report. And that's all for part 2. Thank you.